Welcome to this FloTHERM demonstration. We'll be going over the capabilities of 3D CFD software FloTHERM, which is an electronics cooling specific product, that has lots of features and functionality for importing and utilizing EDA data for electronics. This is what the view window looks like for FloTHERM. On the left-hand side, this is what we call the project manager. This is where we set up all of the geometry and the solution parameters for the analysis. And over on the right hand side we have the drawing board, and this is where we create, manipulate and look at the geometry to make sure that everything is as we want it to be. The basic building blocks in FloTHERM are something called cuboids. So for example, I can create a very quick cuboid like so. I can view this in solid frame, and I can resize, relocate and change all of the aspects of this particular cuboid. And onto this cuboid we can attach things like materials, for example. Let's change this to copper. And we can also attach thermal attributes, radiation attributes. So yes, this is the basic building block in FloTHERM. If we want to make more complex parts, we need to create that out of a series of cuboids. So for example, I can just use the control drag button here to create a more complex shape. And this is how we add complexity into the model inside of FloTHERM. So the options for the user are to either build the geometry from scratch. So you can, as I said, build geometry using cuboids. Alternatively, you can actually import geometry using various plugins that we have in FloTHERM. The first one that I want to show you is something called the FloEDA bridge. So the FloEDA bridge is a PCB import tool. So it can pull geometry directly from various PCB programs such as Mentor Graphics Pads, BoardStation and Expedition. We also support Cadence Allegro and Zuken CR5000. We also have the IDF link, so we can pull in neutral PCB data via IDF as well. But in this instance, I'm going to import data from Expedition. So Expedition is Mentor Graphics' flagship PCB product, and from that we can export something called a FloEDA file. So let's just load that into the software. So the FloEDA file effectively has the PCB shape, size, cutouts. It also has component shape, size, location, and also height information, which is important. So if I look at this in 3D, like so, I can spin that around, make sure that I've got my PCB with all the components in the correct location, like so. Now let's just change the view back to the top again. So we can start to work on this PCB and add more thermal data. So as I said, at the moment this PCB doesn't have enough information for us to perform a thermal analysis on it. So the first thing I need to do is I'm going to change the view from default to something called the modeling level. And when I do that, you'll see that all of the components on the PCB are colored blue at the moment. That means that they are modeled as simple blocks. Now it's taken the component outlines and applied that onto the PCB. There is no information about what's happening inside the PCB, inside of the components. So these are just simple cuboids. There's no junction or substrate or ball grid array or encapsulant. It's just a single block on a PCB. Now we can increase the resolution from a simple to something called a 2-resistor model. Now a 2-resistor model is often, the information for this is often supplied by manufacturers. I'm just going to open up a datasheet from Altera, for example. But if I come down here, you'll find sometimes on data sheets the θJC and θJB thermal resistance values. Now these are thermal resistances which have been standardized by the JEDEC committee. So the test standards are standardized, and under these conditions that JEDEC specified, then the thermal resistance from junction to case will be 0.36 degrees C per watt, and the junction to board resistance is 4.19 degrees C per watt. So this assumes, this is something called a 2-resistor model, and this assumes that the heat either goes up into the case or down into the board. Now because this value is actually lower, I'm assuming that this chip is designed to have a heat sink on top of it. Okay, so because all of the heat is designed to be extracted from the case. So let's use that information directly within FloTHERM. So I've selected my U1 component. I'm going to change it from a simple component to a resistor. Okay, you see the color changes because this is now a thermal resistor network, and now I can specify my junction to case resistance, which is 0.36, and my junction to board resistance, which is 4.19. So like this, I've added a bit more detail into this critical high power component. Okay, now I can do that for all the other components as well. If you have a library of commonly used components, then we can store those inside of FloTHERM. Now, if I click on this part again, for example, you'll see that I've got a package name here and also a part number. This is populated from your EDA tool. Now, if you have this information and it matches the name or the part number in your library, then you can automatically swap these out with more detailed representations. So that's what I'm going to do now. So let's go to the component library swap. I'm going to choose my library folder with all of the components that I'm interested in. And when I hit OK, you'll see that it automatically switches them out. So based on the part number or the package name, it will switch those out with more detailed representations. This one here is actually a detailed package. So we have another product called FloTHERM.pack, which is used for creating detailed thermal representations of packages, and you can download those and use them directly inside of FloTHERM. So this is a fully detailed component with the silicon, die attach, substrate, ball grid array, encapsulant, lead frame, absolutely everything. Okay, so there we have a better thermal representation of our ICs, which are obviously the heat generating components in the system. Next, let's change the viewing level to power. Okay, so at the moment, none of these components have any power assigned to them. So you can see 0 watts, 0 watts. I can manually assign power. So for example, I can put 10 watts on here, I could put 2 watts on here, and I can assign 6 watts over here. Okay, now I can do that, but if there's a lot of components, that's going to take a long time for the user to import all of that information. So rather than that, I'm going to apply something called a power list. Okay, so a power list is simply a CSV file which has the reference designator and then a number. Okay, if I open this in Notepad rather, so let's open that in Notepad. So you have reference designator, comma, number. Okay, if I come down here a little bit further, you'll see I've got U1, 8.8, which means that on the U1 component, I'm going to be dissipating 8.8 watts. So let's apply that onto our PCB now. It will overwrite anything that we've assigned prior. So let's go File, Import, Import Power List. Okay, so I select my power list, which I've already got in the right folder for. Okay, and it'll go through and assign all the powers onto the components. So here you can see my U1 8.8, U24 1.1, U14 0.6, and so on and so on. So like this, I very quickly assign the powers onto my components. The next thing I need to do is actually filter out some of the components which I'm not so interested in. So you can see I've got lots of passive capacitors, resistors, items which, although necessary for the electrical design, they are not really significant for the thermal analysis. Okay, so all they're doing really is taking up geometry and therefore mesh and therefore solution time. So we want to filter these smaller components out of our analysis. So we can do that very quickly using the filter components option. Now I can filter based on based on the package dimensions, if it's got a certain height less than a value, for example, or if the reference designator contains certain letters. So, for example, I'm going to be filtering components that have an R, a C, an L, and a P in the name. So that's going to be resistors, capacitors, LEDs, connectors. Okay, so let's click Filter. You can see it's just taken out all of these smaller components and just left me with the larger components in the model. Okay, so let's check, let's go back to the default viewing level. And the next thing I want to deal with is the layer definition. Okay, so let's look at this in 3D. Now this board is actually a 6-layer board. I'm just going to zoom in to the actual layers themselves a little bit more, like so. Okay, a bit too much. Okay, so you can see I've got 6 layers here, so I can expand the layers. I've got, let's just equispace those. I've got layers 1 through to 6, 1, 2, 3, and each of these have varying thicknesses, okay, measured in ounces of copper. And also you'll find that there is something called a percentage coverage on here. Now let me explain what that means. So the percentage coverage is it's extracted the trace information from the EDA tool, and it's done some visual post-processing on that to determine how much of that image is copper and how much of it is FR4. And it's determined in this instance that we've got a 13% coverage of copper. Now we can go one step higher than that and actually right-click process the layer. And when I do that, I can see the actual original trace image here. It's a black and white image. Again, black is copper, white is FR4 or not copper. Okay, and from the processing on this image, we've determined that it's 13% coverage of copper. Now I could leave it at 13, or I can actually start to localize the copper on this particular layer. So we can't use the information directly. We use a pixelized representation of the actual geometry. So if I move this slider bar over to the left, you can see I get a much finer representation. The pixels are smaller. If I move it over to the right, you can see that it's a much coarser representation. Now, where to set that is, we cover that in the training course. Each one of these pixels has a different copper FR4 ratio associated with it, so it's a different material. So the darker patches will be more conductive than the lighter patches, for example. Okay, so but for demo purposes, I'm going to keep it quite coarse and just create the patches. And you can see on this top layer, I've localized the copper where there is a higher copper density. If I look at one of the central layers, which will be a ground plane, you can see I've got 90% coverage of copper. If I view that, you can see it's almost exclusively copper, so I'm actually going to leave that as it is, just as a smeared representation on that particular layer. And the same for the bottom layer as well. I can process this. Okay, look at the traces, and again, localize the copper on that particular layer. Now, it's more important that the top and the bottom layers are processed rather than the internal layers. The reason being is that these outer layers are actually touching, the ones that are going to be touching the air. Okay, so we want to capture the conduction and convection in more detail. The internal layers are just going to be conduction, so they're not as critical. Okay, then finally, one last thing before we move back over to FloTHERM, I'm going to create a heatsink on my component. So I'm going to select my U1 component. Okay, I'm going to go over here and create a new heatsink on here. Okay, so you can see here's my heatsink. Now it's a fully parametric heatsink, so I can vary the geometrical parameters of this heatsink. So let's make this 40 millimeters by 40 millimeters, for example. You can see the heatsink changing shape. Let's make the base thickness 3 mil. Okay, you can see it just got a little bit bigger there. And I'm going to change the number of fins to, for example, 16. Okay, so you can see now I've got a better representation, well, a more accurate heatsink, which I want to use in my thermal analysis. Okay, and also just one thing of note, we also model the thermal interface material between the chip and the heatsink, so it's going to apply a typical interface material at a certain thickness, which is typical for electronics applications. Okay, so this is still the Flow EDA bridge, so we need to move this over into FloTHERM, so we can do that going File, Transfer and Quit. I'm not going to save that for now. And what you have now over here in the project manager is my PCB. Okay, we have all of my top attached components, and down here in the U1 component you also find my heatsink, which I created earlier. Okay, so the drawing board is good for visualizing the geometry, okay, but it's also, we're going to be manipulating a little bit later, but we need to use something called the visual editor, which is the second sub-application that I want to show you. And the visual editor is mostly used for post-processing, so when we come to visualize the results, we're going to be using this heavily, but we can also check to make sure that all the geometry is in the correct location and we're happy with our electronics. Okay, so I'm just going to close that down now. The next application I want to show you is something called the FloMCAT bridge. So the FloEDA bridge is used for importing EDA data. The FloMCAT bridge is used for importing MCAT data. So let's start that up. So this is what the MCAT bridge looks like, and here are the file formats that we support. So we can read in native SolidWorks, CATIA Pro-E, or Creo as it is now. We can also read in neutral file formats like IGES, STL, SAT, and STEP. So I'm going to pull in a SAT file, and the SAT file in this instance is actually going to be the geometry for the casing of my PCB. So I can spin this around. This has been developed by the mechanical engineering department. Okay, so this is going to be just some simple sheet metal, and I'm going to look at this one piece at a time. So I'm going to select my top casing. Okay, I'm going to select this button here, which will top it or just view it in isolation. And so here you can see just the top sheet metal part. Now, FloTHERM, whenever possible, it's a good idea to simplify the geometry. So any non-Cartesian surfaces have been highlighted in pink here, or magenta. Okay, if I zoom into these holes over here, you can see that we've got some fillets on here, and these are what we call non-Cartesian faces. Now, whenever possible, we want to simplify these. We can deal with complex geometry, but it's very should we say, intensive on the solution, so we want to simplify it and avoid it wherever possible. So in this case, I'm going to do that using the global simplify option. I'm unchecking everything except remove non-planar faces. And what that will do is it will look at the geometry and basically remove all of the non-Cartesian faces and square everything off for me. Okay, so here we have that geometry like so. Now I need to dissect this part into a series of cuboids. Okay, so I'm just going to tick off all of these other options here, and it's going to basically break this part down into a series of cuboids like I showed you at the start. So here we have my top casing like so. Now I'm going to transfer that over to FloTHERM. Okay, and we're left with the rest of the MCAT assembly. I'm going to come back to this very, very shortly, but let's have a look at this top casing and what it looks like. Again, I'm going to top it, which will isolate it. Okay. F6 will expand all of my parts, and you can see my cover is just a series of cuboids which have been dissected to represent that original part. So let's have a look at that in the visual editor as well. Okay, so you can see this is my part, which is just a series of cuboids connected together. Now, if I was to, for example, change the material here, I'm going to just use the drop-down list, and I'm going to load from the library. Let's go FloTHERM Libraries, Materials, Alloys, and choose Aluminium 6061. Now, when I double-click this, you'll notice that it automatically attaches in the material. So double-click, it will attach aluminium, and check it in the visual editor. There we go. Everything is now assumed to be aluminium. So that's a good example of showing you how you can apply different materials to different cuboids if you want, or an entire sub-assembly. Okay, so let's go back to my FloMCAT bridge and deal with the other parts here. So I'm going to use exactly the same process for this bottom case. So again, let's top it. And rather than modeling these holes directly for the fan, I'm going to deal with these over in FloTHERM rather than trying to decompose these and actually model the holes in detail. So I'll come back to these very shortly. You'll also notice on the corners here we have these little fillets. So again, I'm just going to simplify and remove the non-planar faces. So what that's done is it's just turned it into just basically a U-shaped piece of sheet metal. I'm going to again dissect it. OK, and then transfer that over to FloTHERM. So now, again, if we check that, we have our casing. and the top part, the top case, and the bottom case. Okay, and they connect well together. Right, flow MCAT bridge. Now what I'm going to do, this is the placeholder PCB. Okay, so this isn't actually the PCB we're going to use. We're simply going to use it as a placeholder where I'm going to move my detailed PCB into. Okay, so by selecting it, I'm also going to control select these standoffs like this. Okay, rather than simplifying these components, I'm going to use the replace with single object option. Now, when I do this, it's going to look at the outer dimensions of these components and basically attach a cuboid onto them. So you can see now it's changed all these components into blue. I'm going to move these over into FloTHERM. Not worried about the screws. Next, let's look at the fan. Again, very high detail fan. We've got the blades, we've got the hub, the motor, everything's in here. But I don't need this information for my thermal analysis. I'm going to replace this detailed fan with a compact fan. So again, I'm going to replace with a single object. This time, I'm going to select a bounding fan object. Okay, so it's going to look at the outer dimensions and replace that with a simple fan. Okay, it's just green for now, but if we move this over into FloTHERM, I'll show you what that looks like. So I've got everything I need from Flow MCAT Bridge, so I can close that now. So let's look at that geometry in the visual editor. So I've got my casing. If I hide the top, so select the top, F12, you can see that I've got my fan. You can see it's higher detail now. I've got my placeholder PCB. If I hide the bottom as well, you can see the standoffs, and all of the MCAT data has been translated, and everything is made out of aluminium at the moment. Okay, so the next thing I need to do is actually position the PCB correctly relative to the casing. So if I check this now, you'll see the PCB is sort of cutting halfway through. It's at 90 degrees. It's not in the correct location. So I can use the drawing board to actually get it into the correct location. So by isolating the view here, I'm going to expand over here in the project manager, find my placeholder PCB. Okay, expand my PCB over here. Here's my PCB. So I need to do some rotating and relocating to get everything in the correct location. Now it's important that you select the assembly when doing the rotating. Okay, so we're going to be rotating everything underneath this assembly. So select the assembly. I'm going to rotate clockwise, like so. And then I'm going to use my selection mode to just drag this over so it's in the correct location, and it will snap into the new place. If I view this in, let's go back to full views. Let's view this over here. It's not quite aligned in this direction, so I can just click, drag, and now my PCB is in the correct location. Okay, now that I've done that, I don't actually need my original placeholder PCB, so I can either delete it, or I can just disable it, or deactivate it. Okay, so you can see these red marks here on that part, which is now disabled. The good thing about disabling is that I can bring that geometry back if, for whatever reason, that I might need it. Okay, so now you can see that my PCB is in the correct location, and we're looking good. The next thing I need to do is deal with something called gridding. Now, gridding is a way of breaking the computational domain down into small grid cells where we solve the Navier-Stokes equations at each one of these grid cells. Okay, now gridding is a trial and error process, but think of it a little bit like a digital picture. The more grid cells that you have, the finer the end result is going to be. Yeah, the more accurate, the crisper the image is going to be. So we can do that directly inside the drawing board. Okay. First thing I'm going to do is just resize my system. So the system is the computational domain, or basically where the air and the heat transfer is going to be calculated. So I just want this to be a little bit bigger than the actual geometry itself. Okay, so I'm just resizing it like this direction, and this direction. Okay, I press T on my keyboard and that will refit everything for me. So my geometry is now fully inside of my computational system. Now if I press G on my keyboard, I can turn the grid on and off. Okay, so let's just concentrate on this view here. Okay, now you can see the Cartesian nature of our grid. So each one of these grid cells, one of these squares, represents a grid cell. Okay, so we can have finer grid cells. Over here, you've got one very, very large grid cell, and around the heatsink, we've got a much finer grid as well. Okay, if I just expand everything using F6, then you can see my PCB, my heatsink, my fan, everything in very high detail, like so. Now, at the moment, this is a very, very bad grid. My number of grid cells is about 720,000. Okay, but my aspect ratio is almost 2,000 to 1. That means that we're getting very, very thin, long grid cells. This is not ideal. That can cause instability in the solution. Same with any product. So we need to control the grid a little bit more. Now, the easiest way of doing that is to apply something called grid constraints. Now, I'm selecting the root assembly, and I'm going to create a volume region. Now, a volume region is basically a 3D volume in space. Okay, it doesn't actually exist. It's not geometry. It's just a region which we can apply and control grid with. So I'm just going to make my region a little bit bigger than my geometry, like so. And in the other direction, make it just a little bit bigger than my casing, like this. Let's go back to this view. Okay, and once I've done that, I can attach something called grid constraints. Okay, so let's go to my attachments. Here's my grid constraint, and I'm going to create a new one. Okay, so what I'm saying to the software is, inside this grid, and let's call this case grid. Inside this grid, I want you to have a maximum grid cell size of, for example, 10 millimeters. So you can see it dynamically changes the grid. I would say that's not enough still, so let's go down to 7 mil. Okay, maybe a little bit lower, 4 millimeters, like so. Okay, we can go down to 1 if we want, but I would say that's overkill. So let's go back to 4 millimeters. Okay, and that's controlling the mesh inside of that particular region. Now you can see it's actually bleeding all the way to the edge of the computational domain. We don't want that, so we have the option here under location of localizing that grid. So localizing it, watch this number down here, so it's about 1400 to 1 aspect ratio. When I localize it, now we're down to about 300 to 1. So that's much, much better. And here we have some very large grid cells over here, so we can just go back up to the system grid, and again we can set a maximum size. So let's change that to millimeters and change that to 14, for example. Okay, so we got a much coarse mesh, medium mesh, fine mesh. Okay, and this is how we create nested grid elements to control the mesh around of our geometry. Okay, once we've done that, we're basically ready for the analysis stage. One last thing we need to do is to control the fan. Okay, so at the moment the fan does not have any information. It's just the geometry and the location of that fan. So we can replace that with a more detailed library item. Okay, I can go to my library. Let's go to here. Let's clear the filter. Let's go to fans, axial, Pabst. Let's choose the Pabst 412. Okay, I'm just going to drag that over into the fan housing assembly. Okay, so you can now see I've got my fan. I need to position it correctly, so overwriting my original one, like so, and in this direction as well, like so. And also, I want the flow to be in the opposite direction. So let's just rotate. Let's just undo that. I need to select this window so we have a red border around it. Okay, select the fan again and rotate it twice. Okay, and then finally I'm just going to disable my original fan. So when we look at the construction of this fan, you'll see that we have the fan curve. So this is manufacturer data. We have the swirl, the RPM, and the non-linear fan curve from the manufacturer. Okay, and at this stage we are ready to solve. So I'm not going to solve it live. This model takes approximately 30 minutes to actually complete. Okay, there is a parallel version of our software, so you can choose how many processors that you want to use during the solving stage. You can send solvers off to different computers in the network if you wish to as well. So let's load a project which I've already solved. Okay, so if we open the visual editor now. Okay, so I'm going to go through these one at a time, but you can see we have the airflow patterns here, looking at the velocity, the airflow coming in, and I've also got a temperature plot on the heatsink. So let's look at these one at a time. I'm just going to turn off my particles. I'm also going to select my root assembly, and then wireframe everything. Okay, and let's press Y on the keyboard to look normal, straight down. So let's create, first of all, a plane plot. Okay, so plane plots look at the model in 2D. I'm going to change my units to degrees F here. Okay, so by mousing over, I can see exactly what the temperature in various locations in the model are going to be. Now I can change the location of this plane by moving the slider bar up and down. You can see the cool air being dragged in from these slots on the side. If I move this up a little bit further, you can see the cool air over here a little bit better. So over the heatsink, I'm getting 185 degrees Fahrenheit, and the ambient air is 95. And the ejected air from the fan is up at 113. Okay, so we can position this anywhere we want, even through the PCB itself. So for example, these RAM chips, 176, 177, 197. So pretty warm in the middle there. Now it's not just temperatures we can look at. We can also look at, for example, other scalars like speeds. Just a moment. Change that to speed. Okay, so this is now showing us the airflow velocity in the model. So you can see these little jets being generated as air has to cross through here, and a very high-speed jet around the fan, which is obviously extracting the air. Okay, now the air is obviously going to be wanting to come through these set of holes because this is the path of least resistance, and then expelled out through the fan over there. And again, we can move this anywhere inside the model to visualize the airflow. You can see the air is actually hitting onto the side of this heatsink and actually bypassing it quite a lot. Air is not going to want to go through the heatsink because that's obviously quite difficult to do so, and there's a pressure drop associated with it. We can also show the vectors as well. So this is the airflow vectors. So let's turn off the scalar. Okay, and we can see exactly how the air is moving around the heatsink and inside of the model. Again, plotted by speed over here. Okay, so that's 2D plane plots. What we can do next is something called surface plots. So I'm just going to dig down inside my PCB and find my heatsink, top attach heatsink, heatsink, and I'm going to create, let's view this from the top. So isolate the view, just the heatsink, and I'm going to create a surface plot on here, looking at temperature. So I can visualize what the temperature variation on the heatsink looks like. So you can see I'm getting a range from 186 to 182. Okay, and again I can just mouse over and it will tell me what the instantaneous temperature at that location is going to be. Now I can do that for any component in the model. Let's go back to wireframe. let's reset the view. Find my PCB. Yeah. Oh, let's isolate it. Go top. And then plot the temperature variation on that. Okay, so now we can see on my PCB, I'm getting a temperature variation between 102 and 194. So quite a high temperature gradient across this PCB. Okay. Again, let's go back to wireframe. And then finally, I'm going to show the casing. Okay, so let's choose the cover and the case. And this will tell me, let's top this, choose the cover and the case. And this will now tell me what my touch temperatures on my casing is going to be. So I'm getting a variation from 100 to 104. Yeah, this corner is going to be the hottest. And the other side of the box is going to be the cooler side over there, near the vent holes, where the air is rushing in. Okay, so that will allow you to determine what the touch temperature of your product is going to be. And then finally, let's just reset the view. Go to the root assembly. Let's make it solid. Okay, and we can show the particles. So particles show how the flow moves dynamically, how it moves through the model. Again, we're getting a lot more flow through these vents than this side. Okay, again, path of least resistance. And the nice thing about these particles is that we can animate these if we want, and we can show how the air is dynamically moving. So you can see the swirl on the outlet. This is colored by speed at the moment. I could change that to temperature, okay, and we can see how the air heats up and is then expelled out through the fan, like so. So our hottest air temperature is up at 124 degrees. If I wanted to get numerical results from the software, I can also do that by using the tables window. Okay, so I'm going to plot the tables below the geometry. And this is the numerical information from the software. Okay, so you can see this is the number of iterations, okay, versus the actual temperature. So if I come over here, I can find my U1 junction temperature, 200 degrees, case temperature, 197, okay, and all of my various components that I've pulled in from my EDA, the Flow EDA bridge. So each one of these components is reporting a different junction temperature. If you wanted to, we can also extract this data out into Excel. By right-clicking and exporting this to Excel. So I can click Run Spreadsheet Application and paste selected data, and that will push that out to Excel for you. Okay, so that was the process of creating the geometry by importing EDA and MCAT data, positioning everything together, meshing, solving, post-processing, both visual and numerical, and this is the steps that you go through to do the analysis. The next stage is to actually perform an optimization of this geometry. Okay, and we can do that in FloTHERM using something called the command center, and let's do that now. The command center, I've already set this up, but the command center allows you to take advantage of the base parameters. And if I just filter over here, what I'm going to be doing is I'm going to be varying the heatsink data. So I'm going to be changing the number of internal fins. So I'm going to be varying this between 6 and 18. Okay. The fan location, I'm going to be changing it so the X location will be between 5 and 100 millimeters. And what that's going to do is it's going to change the heatsink parameters and the fan location. And I can check that graphically. Okay. And zoom into this view over here. This is my original model. And if I look at my different design points, you can see the fan is moving and the heatsink parameters are changing as well. So what the software will do is it will try all these different solutions to try and work out what the best combination of these two input parameters will be to give me what my lowest junction temperature will be. So my key here is to reduce my U1 junction temperature as much as possible. I have a scenario table with all the different design points, and you can see straight away design 3 is giving me a 20-degree difference in temperature. So if we visualize what design 3 looks like, design 3, so you can see I've got much higher fin density and the fan is almost in front of that heatsink. So just by moving it over here, we're going to be getting a 20 degrees C temperature difference. So we can have any number of input variables, any more than sort of 3, and you're going to have a long time solving. But as long as you can put in your optimization input envelope, then the software will find the most effective combination of those to give you the coolest electronics.